Hello, everyone. So this is um we're going to continue our discussion on distillation, which is our third module for the prelim. Okay, so let's last time we discussed about what's distillation column. What is distillation column or what is distillation process? Then we've discussed as well various types of distillation. And then I've already given you as well seat work on this. And then after that, we've discussed about um, ma the summary of distillation technique. So now we're going to discuss the methods of distillation. So you have the single stage distillation. So it's the liquid mixture is boiled. So simply it's just boiling. Your liquid is charged to a heated kettle and then it's being boiled slowly. And then your vapor naman, it's withdrawn as rapidly as they formed in your condenser. So that's the single stage. And then you have flash distillation. So yung flash distillation, it's a liquid mixture and it's partially vaporized. So there's um a vapor liquid equilibrium occurrence and then you have the bottom and distillate being separated. So this is flash distillation. Your liquid is being vaporized and then after that there's separator. And then there's also what you call simple batch or differential distillation in which your liquid is boiled slowly and then it runs through your condenser and it's collected there. So there's like a rich, more volatile component in your condenser. And let's talk about relative volatility. So, relative volatility, it's an important parameter because it dictates how easy or difficult it is to separate your two components in a mixture via distillation. So, as you see here in the diagram, we have a setup for batch distillation, which includes components like the batch still, you have condenser, and then you have your product receiver here. So, basically, your relative volatility, it's denoted as Greek letter alpha. And it is a measure that tells about how the ease of your separation of the two components based on their volatility. And it's calculated using this equation here. So you have alpha 1, 2 is equal to K1 divided by K2. So K1 and K2, it is the equilibrium constant for component 1, component 2, respectively. It is equal to Y1 divided by X1 divided by Y2 divided by X2. Y1 and Y2, they are the mole fraction of your component in vapor phase, and then your X1 and X2, it's in the liquid phase. So if you're going to derive Y1 from this equation here, you can transfer Y1 or you can transfer the denominator. Sorry. Can transfer the denominator here above. So this is what happens if you're going to solve for y1. You have y1 is equal to alpha 1 2 x1 divided by 1 plus x1 alpha 1 2 minus 1. Okay. And again, this equation, it helps us calculate the mole fraction of your component 1 in your vapor phase, which is important for understanding how effective your distillation process, how effective it can separate component 1 from component 2. So the higher your alpha or your relative volatility, the greater the difference in your volatility between your two components, which generally leads to a more efficient separation process. So again, this principle is very important and it's a fundamental when you design your distillation processes for industrial applications. So here are the key concepts of vapor liquid equilibria, which we have discussed last meeting or last week. So the fundamental, which they are the fundamental in understanding how mixtures behave under varying temperatures and pressures, particularly if you have a distillation process or even other separation processes. So you have the Raoult's law, and then you have the Henry's law. So these are the two important laws in your liquid vapor equilibria. So your Raoult's law, it states that your partial pressure of your component in your mixture, it is proportional with your mole fraction or your XA in your liquid phase times the vapor pressure of your pure component, which you can use your Antoine's equation in determining the vapor pressure in your pure component. So this law or the Raoult's law, it applies to ideal mixture where the interactions between your different molecules are similar to those in your pure substances. Another one is you have the Henry's law. So yung Henry's law, it applies to dilute solutions, and then it relates your partial pressure of your component to its mole fraction by a proportionality constant, which is the Henry's constant. So that is Henry's law. And then you have Dalton's law. It's important to calculate your total pressure, which is PT, total pressure, um, total pressure of your gaseous mixture, and then your partial pressure of each gas. So you have, in this case, you have PA. That's the total pressure. That's the partial pressure of component A. And that is equal to PTYA, or the mole fraction of your gas in the vapor phase. And then you have your K value. So your K value, or the equilibrium constant, it's important for determining how much of your component will be in the vapor phase compared to your liquid phase. So yung kanina, to calculate your relative volatility, you need your K value. So, or your equilibrium constant. So, for an ideal system, yung K value, it is the ratio of your vapor of that component to the total pressure in an ideal system. So this is the formula. The vapor pressure of component A to the total pressure in an ideal system. If you have a dilute system, it is the K value is the Henry's constant of your component A divided by the total pressure of your system. And then you have the relative volatility, which is, again, it's the measure of the relative ease of separation of your two components in a distillation process. So for an ideal system, it is defined as this equation, YA times 1 minus XA divided by XA times 1 minus YA. And then for dilute system, you have the partial pressure of your component A divided by the partial pressure of your component B. So you need to understand these fundamental principles so that you can design and optimize your separation processes by predicting how different components in a mixture will behave under certain conditions. So So one of the most integral pieces of equipment in chemical processes industry is your fractionating column. So your fractionating column, it's essential. It is essentially a vertical shell where your separation of liquid component is based on their boiling points. So you have the key components for your column here. You have your column internals or your um, equipments here inside your column. So one is your column trays or your plates or your packings. So these are installed inside your column to increase the contact surface between your vapor rising through the column and the liquid as well that is descending. So this contact, it helps achieve equilibrium stages where the vapor and liquid phases, they exchange constituents, which enhances your separation efficiency. Another key component inside your column or in your column is the reboiler. So here. So yung reboiler, it is positioned at the base of your column. So yung reboiler, it provides the heat to vaporize your liquid, to vaporize the bottom liquids. The vapor that is generally generated here, it ascends through your column, which facilitates in separation process. And then another component is your condenser. So your condenser is located at the top of your column. So yung condenser, it cools your vapor that leaves your column, which converts the vapor to liquid. So this liquid is known as the distillate and it's collected as a product dito. And then you have your reflux drum din. So yung reflux drum, it holds the condensed vapors inside your condenser and then it allows for the control in your reflux. So reflux is the liquid that is returned to your column to maintain the desired level of separation. So we're going to discuss why there's reflux, why is it necessary in your distillation process, and how it helps your distillation process. So there are sections as well in your fractionating column. You have your enriching section, which is located above your feed point. So yung section na to, it is enriched in vapor, and yung heavier components, it's already removed and minimized in this part na. Because those components, they are condensed and then they return as liquid towards the bottom. And then another part is you have the stripping section, which is below your feed point. So yung stripping section, it helps remove lighter components from your descending liquid. So which allows them to rise as vapor due to their low boiling point. So here you have the feed, which is the mixture that needs to be separated. You have the distillate, the vapor that has been enriched and condensed, and then you have the bottoms. So yung bottoms, it's the heavier part of your feed, which is concentrated at the bottom of the column. And then you have your reboiler, which is the heat in. You need to introduce heat here, provides the necessary heat for vaporization at the column base. And then you have the heat out naman, which removes the heat from the condenser to condense the vapor into liquid. So understanding how each part of these fractionating column functions is very important for designing and operating distillation processes effectively. So it enables you students to optimize the separation of components to meet your desired purity and yield. So let's go back to our concept about vapor liquid equilibrium or VLE, which is a fundamental principle in your designing and operation in distillation column. So yung VLE, it describes the conditions which yung vapor and yung liquid, they are in equilibrium at a given temperature and pressure. So meaning, if you are going to talk about phase equilibrium, the rate of evaporation and the rate of condensation, they are the same because they exist in equilibrium. Yung phase nila is at equilibrium. So, this equilibrium, it's important in designing processes, separation processes like distillation. So, yung distillation column, they are based on the boiling point properties of the components in your mixtures. So, the sizing and the height of your columns, they are important and are determined by the VLE data of your mixtures being separated. So, understanding VLE allows you to predict how your components will be separated under different conditions of temperature and pressure. So, it's very important, and it can be obtained from the boiling point diagrams under fixed pressure or under fixed temperature. So, if you have the VLE data, it shows the composition of your vapor and your liquid phase as it changes with temperature or as it changes with pressure. So, if you have a binary mixture, yung VLE mo, it's represented as a plot showing mole fraction of one component in a liquid phase versus a mole fraction. So like this one, Y versus X diagram. So yung curve dito, it represents as the equilibrium states of your mixture at constant pressure. So yung x-axis represents the mole fraction of your component in liquid, and yung y-axis naman, it represents the mole fraction of your vapor. So yung line dito, it represents line XY, in which it indicates where your mole fraction of your vapor component phase is equal to the liquid phase. So that's why. So yung equilibrium line or the equilibrium curve, it indicates the components of your liquid and vapor that are in equilibrium in a fixed pressure. So this, so how do you determine the mole fraction? So yung mole fraction, yan yung ginagamit para ma-express yung concentration ng isang component sa mixture mo. So it is defined as the number of moles of a specific component divided by the total number of moles in the mixture. So for a binary system, if you have a component A and component B, yung mole fraction of A in your liquid phase is calculated as the moles of A in liquid phase divided by the moles of A plus the moles of B in the liquid phase. Same lang din sa vapor phase. So the mole fraction of A in vapor phase is equal to the moles of A in vapor divided by moles of A plus moles of B in vapor phase. So several physical chemistry laws that are used to determine the VLE diagram is, again, yung Dalton's law, yung Raoult's law, and then yung Henry's law. So now let's going to discuss the operation of a typical distillation column. So we are going to focus on critical role ni trace ng vapor and liquid interactions, and then ano yung mass and heat transfer processes involved in the distillation column. So let's first focus on the structure of your distillation or fractionating column. So dapat cylindrical in structure siya. So, and then yung fractionating column mo din, it's divided into sections by trace. So yung column is divided into sections by trace, which is critical for the separation process because allowing for multiple stage of contact between the rising vapors, it helps in your separation process. And then, ano yung function ni trace mo? So, there is sieve trace din in between your sections. So, it's called sieve trace or perforated trace. So, yung trace, they are usually perforated, or they are also known as sieve trace because these perforations, they allow vapor to rise through the liquid sitting on the trace, enhancing contact and transfer processes. So as the liquid mixture is heated, yung vapor mo, it rises from the bottom of the trace. From the bottom of the column through these trays towards the top, carrying it with the most volatile components. And then yung meron naman ding liquid that flows down from the top across the trays, which is guided by the structure known as downcomers. So these are specifically designed to ensure a controlled flow of liquid back to the bottom of the column. So there is a continuous flow of liquid interacting with vapors, which is essential for achieving desired separation. And then there is mass and heat transfer. So because at each tray, an equilibrium of mass transfer is established where your components of higher volatility transfer to the vapor phase and less volatile components remains in the liquid. So there is a mass transfer in between the processes and also heat transfer. There is a heat transfer at the hot vapor from your bottoms, which heats the descending liquids. Yung mga pababa na liquid, due to gravity, it's heated by the hot vapor. And then yung liquid, then it cools the rising vapor, which is hot rising vapor. So there is heat transfer. So yung rising vapor comes in contact with your downflowing liquid in each tray, allowing for the exchange of heat and mass. So that contact in between the two phase, it's very important for reaching equilibrium in each stage, which determines the efficiency of your separation process. And that's the importance of trays because yung tray, it increases the surface area of interactions. So making separation processes more efficient by allowing for a finer distinction between your different components based on their volatility. And then there's in your distillation column dito, the vapor that reaches the top is the most volatile component. So yung vapor, it's being withdrawn. And then yung withdrawn vapor, it undergoes condensation. So either it's fully or partially, depending kung ano yung design ni system mo. So yung condenser, it cools your vapor and then it turns back to liquid form, which is what you call distillate. And then dito, you have your reflux operation. So yung reflux dito, there's what you call the term reflux ratio. So basically, yung reflux ratio, it dictates the amount of the liquid na babalik sa column mo versus the amount that is taken out here in the product. So that's why it's called reflux ratio because yung liquid na babalik divided by the liquid na mama-produce or yung product liquid or yung yield ng product. So that is ratio. It's adjusted para ma-optimize yung purity and yung yield ng product. So what's the purpose of reflux? So, ang primary focus ni reflux is para ma-ensure na continuous yung vapor and liquid contact above your feed tray dito. So, that's why kailangan din na may maibabalik na portion ni component A dito kasi it's important para may continuous na vapor liquid contact above this tray, above the feed tray, I mean. So there's a proper balance of heat and mass transfer. That's why may mabalik na component A din dito sa enriching section mo. And then, yung reflux din, it helps enrich the rising vapor with more volatile components by repeatedly condensing and vaporizing the mixture. So that process, it enhances the separation efficiency and purity of your overhead product. So now let's go to managing the bottoms and the feed stream as well. So ano yung nasa bottoms product? So at the bottom of your distillation column, dyan yung less volatile component or yung mga hindi ga-vaporize easily. So dyan sila mag-accumulate. So this mixture is referred to as the bottoms product. So part of this bottoms product, it's is periodically drawn out as a separate product. That's why usually in a petroleum industry, yung mga heavier oils, nandito sila sa bottoms. Gina-drawn off sila periodically. So, yung mga mabibigat na compounds, organic compounds. So, here, it is heated to generate vapor that rise back up to your column. And this process, it helps in recycling valuable components that can be further separated and purified. So there is recirculation throughout your column. So yung liquid molecules at the bottoms, it will come in contact, into contact with your vapor as it rises through each tray here. And this contact, it facilitates the transfer of heat and mass as well for the allowing enrichment of your vapor with more volatile components. So there's a continuous recirculation. And then you have your feed stream. So yung feed stream, it's introduced continuously to the column at an intermediate tray. So this point is strategically chosen where your liquid composition closely match. So hindi lang siya basta-basta nilalagay kahit saan yung feed. Gina-calculate din kung saan siya ginalagay. Kasi para ma-optimize yung ma-optimize or ma-efficiently manage yung energy and mass balance mo. So that's why there's an optimized feed location. So the part of your column above your feed tray is known to as rectifying or enrichment column. And then yung below naman of your feed tray, it's known as stripping section. So the more volatile component is one component in the binary mixture which has the lowest boiling point. And the mass balance over the column would automatically only use the more volatile component. So usually yung ginagamit sa mass balance is yung mga volatile component. So hindi na gina-solve yung mga less volatile component. So yung more volatile component yung mga ginagamit. So thus, if you're going to notice later sa pag-solve natin, may mga values na may mga XF, XD, and XW, it will automatically mean that it is the mole fraction of the feed of the more volatile component. So the mole fraction of the distillate, of the more volatile component and the mole fraction of the bottoms of the more volatile component, or sino yung unang maboil. So yan yung symbol na to is nag-signify siya sa mole fraction ng more volatile component. If there are two components, A and B, and the more volatile component is A, then yung XF, XD, and XW, it's referred to as component A, ha? And in referring to component B, ito yung symbol nila. So it will be XFB, XDB, and XWB for uniformity. So ito na lang yung gagamitin natin. So there's Mccabe-Thiele method. So it's a fundamental graphical technique that's used by the chemical engineers throughout the world para mag-design ng distillation column. But it's a graphical technique. Using Mccabe-Thiele, you can determine kung pila ang number of stages required for separation, kung saan ilalagay mo si feed, stream, and then kung gaano kataas yung distillation tower mo. So, dyan mo ma-determine using the Mccabe-Thiele method. But it's going to use the VLE data. So that's why you should be familiar on how to determine your vapor-liquid equilibrium data. Because this data, it predicts how different components of a mixture will behave under certain temperature and pressure. And then, yung VLE data, yan yung gagamitin mo to determine or to draw your equilibrium curve. So, which is very important in yung Mccabe-Thiele method. So yung yung equilibrium curve mo is kasali siya sa Mccabe-Thiele method talaga. So it's developed, yung Mccabe-Thiele method is developed by Warren L. Mccabe and Ernest Thiele. So it's a straightforward graphical method to design your distillation column. And it's widely taught in engineering curricula. So, before ginagamit na namin to, so it's very famous in the chemical engineering world. So, you should be familiar with this method. And yung method na to, it involves drawing your VLE curve, and then you should draw as well yung operating line mo inside your curve, and then yung intersection points of these lines. So you should be familiar on the steps of this Mccabe-Thiele method. So yung steps, i-plot mo si curve, and then determine feed and rectifying lines. Tapos, yun, gagawa ka na kung saan sila ga-intersect. So we are going to have an example later on how to do this method. So though though it's not used in board exam because this is a graphical method, hindi pwede magdala ng graphing paper during your board exam. But it's very important in chemical engineering because first, it provides a fundamental foundation or understanding on how distillation works. So if you understand this method, automatic makagrasp ka or magrasp mo yung basic principle ni mass and energy balance sa distillation column mo. So that's why it's very important to know Mccabe-Thiele. And then, magagamit mo din to if, for example, if you want to design planta, so you can use the Mccabe-Thiele method because it's widely known, and then hindi siya ganun mahirap, hindi siya nagagamit ng mga software tools. And then, yun, ma-utilize mo yung theoretical knowledge and then ma-apply mo siya sa industrial, magamit mo siya sa industrial application din. So that's why it's very important. And then yun, yung standard na siya na part ng chemical engineering curricula worldwide. So that's why it's very important. So yung Mccabe-Thiele approach, it's a graphical method and uses VLE plot to determine the theoretical number of stages required to effect the separation of a binary mixture, and it assumes constant molar overflow. So constant molar overflow yung assumption ng Mccabe-Thiele, and then molar heat of vaporization are roughly the same. Heat effects are negligible. And then for every mole of vapor condensed, 1 mole of vapor liquid is vaporized. So ito yung advantage. It's very simple. And then you have the VLE diagram of your binary mixture. So ito yung steps. Operating lines are drawn first. Operating lines define the mass balance relationships between liquid and vapor phases in the equilibrium. And there is one operating line for the bottom section of the column and for the top. So use for the constant molar. So ito yung assumption. Constant molar overflow. So let's go back to your general distillation column diagram, which is shown in figure 1.3. So this diagram, this is a general distillation column. So it's divided into 2 main loop section. So you have this here and then sa bottom din. So yung components sa distillation column mo, you have your F for feed. So kung saan yung mixture mo makikita, kung saan yung mixture na gusto mo i-separate, nandito siya sa feed. And then so typically yung feed, it's not located at the bottom or at the top of the of your column, but it's located at a point that maximizes the efficiency of your separation. Which is based on the composition of your feed. So you have your distillate, letter D, and the bottom products, which is W. So yung distillate, where the lighter components are found, and then yung bottom product naman is the heavier components. And then you have your V, which signifies as your vapor flow. Yung vapor that rises through your column. So interact siya with your liquid that is descending on each tray. So this interaction is very important for your separation process. And then your L naman, it signifies as the liquid flow. The liquid that descends from tray to tray. So it's facilitated by your downcomers. So yung descending liquid, it provides a surface for your rising vapor to contact. And then you have your plates. So yung plates is designated as subscript N. Subscript N. So each tray or plate, it's designated by letter N or letter M. So let's have an overall material balance over your distillation column. So your feed. In is equal to out. Feed is equal to distillate plus bottom products. That's why it's F is equal to D plus W. So your F goes in, your D and W goes out. And if you are going to assign the mole fraction, kibali, pag in terms natin yung material balance mo sa more volatile component, you have this equation. So you have F XF is equals to D XD plus W XW. Again, yung mga mole fraction dito, it signifies as the more volatile component. So here, first, let's focus on the enriching section. So if you're going to have a material balance above your feed stream, so this is what happens. You have your VN. So yung vapor na pataas na vapor, which is designated as VN, is equal to D. Kebale, we are going to make a material balance here at the top or above the plate N. Designate as plate N, above plate N. So magawa tayo ng material balance above your plate N. So that's why it's designated as VN is equal to D or distillate plus yung bababa na liquid mo, which is LN plus 1. And if you're going to express this material balance in terms of the more volatile component, you have YN. Y siya because V is vapor. So, dapat naka-Y yung mole fraction mo. So, YN, VN is equal to LN plus 1. Since naka-L siya, so this should be in liquid. So, dapat X yung mole fraction mo. So, LN plus 1 xn plus 1 plus dxd. So, pag gusto mo siya in terms of y, yung whole equation na to, divide mo lang sila, lahat ng terms dito with vn. So, this is your equation na. And then, since we assumed that constant molar overflow or constant moles of liquid overflow mo, so pwede mo mapalitan si Ln plus 1 with Ln. So this is your final equation. So please take note of this equation. And now, let's focus on the loop 2. Dito tayo mag-focus sa baba. Material balance tayo dito sa baba. So you have in is equals to out. So in, yung papasok is si LM. LM. Ang lalabas naman is si vapor. And then yung bottom product mo. So LM is equals to VM plus W. Or ito. Pag i-transpose mo yung variables mo or yung terms mo. And then, if gusto mo siya in terms of your more volatile component, so magdagdag ka ng mole fraction. So, since V2, dapat si Y. And then, since L2, dapat si X. So, ito na yung equation mo. And then after that, if you gusto mo siyang in terms, yung equation ng left side mo is in terms lang ni y component mo. So divide this term with v. So ito yung final equation mo. This is equation 15. Take note of equation 15. Now, equation 15 is similar with equation 14. Diba? Except sa naka-subtract ka dito. So, it gives the corresponding relation between the composition of your vapor rising to the plate and the liquid on the plate for the section below the feed plate. So, yung equation 14 and 15, they are the equations of your operating line. So, the top operating line is a straight line in the form of this. So, this is your equation 14 kanina. So, yung Ln over Vn, it is what you call the gradient at the top operating line equation. And then, yung second term naman dito, which is dxd over Vn, it is the cutoff point of the operating line equation on the y-axis. So, now let's go to your second equation or yung equation 15 mo. So, if you remember or if you notice, yung equation 15 mo, it's a linear equation in which ito yung M mo, this is your slope, and then this is your intercept. So yung slope mo, it's still a gradient, and then yung intercept mo, it's a cut-off point in the y-axis. However, you can yung equation 14 mo, which is this, yung first equation, yung equation 14 mo, pwede mo incorporate si reflux ratio. So, 'di ba, sinabi natin kanina, si reflux ratio is the ratio of the liquid that is returned to your column divided by the distillate. So, which is Ln divided by D. So, this is your reflux ratio. R is equals to Ln divided by D. So, if we're going to focus here on the top operating line, so we have this equation 14, diba? This was derived a while ago. Dapat ma-incorporate natin si reflux ratio dito sa equation 14 natin. So, si V, yung denominator dito sa term na to, and then dito sa second term, pwede mo, yung V dyan, pwede mo siya mapalitan into D plus Ln. After that, yung ginawa ni Mccabe, Thiele, is gidivide nila yung terms, yung first term and second term, divide nila with D. So, after mapalitan si Vn dito, Vn sa denominator, Vn with Ln plus D, nag-divide sila ng D sa numerator and sa denominator. Sa first and second term ni denominator din. And then, since we know that R is equal to Ln over D, so therefore, ma-reduce mo yung equation na to into here. So, na-incorporate mo na si reflux ratio sa top operating line mo, which is in your equation 14. So, from this equation, this is your equation 14, na-incorporate mo si reflux ratio. So, which is this, equation 18. So, yung R divided by R plus 1, it is the gradient of the top operating line in terms of reflux ratio na. And then yung second term mo naman, which is xd divided by r plus 1, is the cut-off point of your y-axis in terms of reflux ratio. So yung equation 18, which is the operating line at the top operating line, in which na-incorporate yung reflux ratio, relates the vapor mole fraction and the liquid mole fraction at the liquid and vapor that is in equilibrium at every stage. Another factor that will greatly affect the number of stages required in a distillation column is the condition of the feed stream entering the column. So therefore, a third operating line is introduced. So 'di ba may dalawang operating line ka na. Yung first mo is na-incorporate mo si reflux ratio, yung sa ikalawa is doon ka nag-focus sa baba after sa feed stream. So kailangan mo ng third operating line. So diyan mo na ma-incorporate yung mga effect ni feed condition sa third operating line mo. So, the conditions of the entering feed determines the relationship between the vapor flow rates in the stripping and enriching section, and the liquid flow rate in the stripping and enriching sections. So, the vapor and the liquid flow rates in the enriching and stripping sections are related in the following manner. So, ito, sa liquid flow rate sa stripping and enriching section, and then ito naman yung vapor flow rate sa stripping and enriching section. So, yung Q dito, that is the heat required to vaporize 1 mole of feed divided by the molar latent heat of feed, or it's also known as the energy required para to bring 1 mole of feed to a saturated vapor divided by the molar latent heat of vaporization. So here, therefore, yung Q mo, magamit mo yung equation na to determine your Q. Q is equal to MCP of your liquid delta T plus gamma divided by gamma. Yung M is always 1 because we work with unit mass. And yung gamma naman, that is your latent molar heat of vaporization. CP is the heat capacity. So, dapat yung heat capacity mo is yung unit niya is kJ per k mole. And then, multiply it with the mean molar mass of the feed. Para makuha mo siya in kJ per kg Kelvin. So, yung delta T dito is yung T ng boiling point minus T of your feed. So, for a superheated vapor, you can use this equation as well. So, therefore, yung isang equation mo is this. So, this equation is what you call Q equation for the Q line or the feed condition line. So, dito, ma-relate mo yung feed mo sa equation na to, your third equation. So, yung Q line equation mo, this is also in the form of linear equation. So, this is your slope or your gradient, Q divided by Q minus 1, and then this is your cutoff point or your y-intercept. So, for example, if your feed